Okay. Welcome to class. Today is October 21st, 10 days away from Halloween. Temperature check. Are you guys doing anything for Halloween? Anybody doing anything? No. Probably no parties or...
No, but I'm confused about what the trick-or-treating thing is going to be. Like, do I leave candy out or not?
It's a fair question. I actually had somebody in our neighborhood design, like they put out they haven't done it yet. They're gonna put out a clothesline and clip a bunch of bags of candy.
Oh,
Like that's a lot of work for what is probably going to be like a 20-second exchange really at the door. What are you supposed to be? Here's candy, but
yeah.
I saw where someone like put PVC pipe down their stair railing and so they can slide the candy down.
Send candy
they're just
down.
gonna shoot it down.
Yeah.
I like to imagine it like those cannons of like t-shirt shooters in arenas.
Yeah.
That would not be friendly.
God.
Shouldn't do that. All right, let's take roll real quick. Haley.
Here.
Cole.
Here.
Zach B. No. Savannah.
Here.
Eliza.
Here.
Eliza, I have to work so hard every time to not say your name as a sing-song from Hamilton. Eliza. Anyway, so just let me know.
I get it. No problem.
Lots of effort being made. Bree. There's Bree. I think she's there, right?
I couldn't unmute. I'm here.
Oh, you're good. Okay. Grace D.
Here.
And Greg D.
Here.
Emily.
Here.
Olympia.
Here.
Jenna.
Here.
I think Daniel said he wasn't going to be here today. Yep. Greg M.
Here.
Yeah, there you are. Ashley. Here. Kyle. You guys, Kyle's not here. Is he good? Okay, you know what that means. No free pass at the lack of participation. We're going to need some of you guys to step it up. All right, Saga.
Here, sorry.
Yeah, no, it's okay. I'm like every time, like just scrolling through all the boxes trying to see the people's names. Ada.
Here.
And Elizabeth. Hello. And Mary Pat. No. Okay. So lay it on me. How was the test?
It wasn't too bad.
Good. Is that everyone's opinion?
I think the Z-score and percentage thing, that was hard for me.
That was hard. Okay.
Yeah, I was a little bit like I recognized most of it, but just the way that it was, I guess like I would get stuck at, if there was like a few, like I'd get stuck at step 2 or something like that, and I would like be so lost as to what the next step was. So, and then I would look back at my notes and it would be like a very simplified version, and I felt like I was missing something.
Okay. Well, the bummer part is I am not done grading because several people, this is totally fine. This is not a complaint at all, so don't take it as that. But several of you just took pictures of the work you did on paper, and everything is turned around. So I'm having to find a way to print it, download it, score it, and re-upload it. So it's just taken me a few more steps, so I'm behind. I am hopeful that I will get it done by Friday so that you guys have updated grades and can see what that looks like. But on the whole, people did really well. So know that part of it. And this is an exam, as I'd mentioned before, if any of you guys, if there's the bulk of the class is missing a question, then I did something wrong in framing the question or even maybe covering it in class. So you guys are not going to be, rest assured, you're not going to be held responsible. If the bulk of the class is not getting a concept, we're going to cover it again, and then it'll be tested again in the next exam. The goal is not to fail an entire class, right? Like that's never the goal, and that's not happening either. So don't think that's happening. So
Are the next test isn't cumulative though, right?
it is not. It's only going to be the chapters that were they're going to be presented from this point on. We're going to talk about estimations and confidence intervals up until the next part. I'm just explaining if somehow there was a concept that was so missed, I wouldn't want to just go, oh, we'll just toss out that question. And I guess you guys just won't know how to do z-scores, for instance. I'd want to go over it again to make sure everybody understood it. The goal is mastery, not to have you guys be penalized on a specific score. That's never, ever the goal. So,
And then
yeah.
if, so I kind of like walked away from the test feeling like I didn't do like quite as well as I wanted to. And I was sort of nervous about that. Just to confirm the tests, even if we didn't feel like we did we got the grade that we really thought we would, it's only worth 12% or.
That's right.
Okay.
It's a smaller percentage. Yes. The labs count, participation counts. So know that going into it. It's not 50% of your grade that goes into an exam either.
Okay.
Yeah, because you get quizzes, the labs, all of that. Yeah. Yeah, and then we'll discuss the lab today. We're going to prep it, and then you guys will have, the lab will be due by next week. And then next week, there'll also be a quiz. Mostly, 100% on the material we covered today. So that should be a fairly straightforward quiz as well.
Okay, and then this is like a paranoid question, but we didn't start any sort of like projects or anything quite yet, right?
No,
Okay.
no projects. No, that'll be much later in the class. Let's see here. Let me just pull it up so we're all looking at the same thing. Oops. Yeah, and again, I don't know how things are gonna look in this world. Just mostly the final project. Let's pull it up here so I can describe to you again. You're gonna analyze a data set, and it's gonna include a lot of the things that we've covered so far in terms of analysis. And then you're going to have to turn in that assignment having been completed. So you are so in the class, the way I've run it before is that I would give all those data sets to you guys in class, and we would run it in SPSS and get some practice with it. The world is different. So I'm gonna give you guys 5 options on data sets that you can select. They're gonna be on Course Connect, and you'll go from there and then ask questions of the data the same way you would if you were a researcher, and then run through the analysis and provide some interpretation. So that's what the final project will be. But it's not a project that you're working on during multiple weeks like you would in another class. It's more, it's considered a final project because it includes really everything we've learned in the class. Does that help a little bit?
Yeah, I just wanted to make sure that like I didn't miss something on the first day where it was like we should be working on it chronologically. It's just a paranoid.
Not at all. Nope,
Thank
not
you.
at all. So what I'm gonna do is the week before Thanksgiving, I will go over all of those, and I'll have you, there'll be a whole description piece where here's the data sets, here are the questions you need to ask, here's what it's supposed to look like, so that you guys are set up and you can be working on that for a couple weeks. It will not take you that long. In fact, the final project, I had that be in the past part 2 of the final exam. So it was just done in class.
Okay.
Okay.
Thank you.
Oh, deep breaths. Okay. Any other questions I can be helpful with? No? Okay. As always, stop me at any time. Our goal will be to go for just a little over an hour again. We'll take a short break and then start up again. All right. So today we are going to be talking about estimation. So let me make sure that you guys can see this well. Where's slideshow? From beginning. Okay. move our faces. Can somebody give me a shout out? Can you guys see?
Yep.
Okay, super. All right, so estimation. What we're going to be talking about today is what are specifically point estimates, what are confidence intervals, and confidence levels. The confidence level and interval, that is the bulk of our coverage for today. And we'll talk about how and why they are so important when we deal with research and statistics at large. All right, so why do we estimate, right? We spent a lot of time talking about sampling before and how we look to a sample rather than a population. So in what way would it be important to know how to estimate?
Estimation can give you a decent overlook of what you're expecting.
Kyle, you're here. I just
Yeah.
finished telling all the students, you're gonna need to step up your game, you guys. Kyle's not here. So part A, let me mark you here. Okay, yes, I didn't even hear your answer because I was too shocked. I had to turn on the video. Go on.
Okay,
Welcome.
so I think estimation is important because sometimes it's too difficult to get such a population, so you kind of have to make assumptions, and estimating kind of gives you a decent trajectory of which direction you're going to go.
That's exactly right. Right. So because we don't spend a lot of time, most of our studies do not revolve around a population, because that is, as we talked about, not cost effective, not time effective, it's not efficient. And frankly, it's not even necessary, because we can use a sample and then estimate what the result would be for the general population. So that is why it's so crucial that we know how to estimate well, because I could certainly estimate, like if I asked you right now, actually this will be fun. If I asked you guys to think, let's find something fun to think about. What is the proportion, or what do you estimate as the percentage of students in your class who are born and raised in Grand Rapids? How would you go about figuring that out?
So the question is, can we ask them questions like, oh, what do you
Okay.
think about Michigan?
What do you think about what?
Michigan? Because then
Okay.
gauge if they are super positive about it or if they hate it, and then you can kind of sway from that.
All right, so rest of the team here, class, what do we think about Kyle's idea? If we ask people, what would that be?
If we ask them directly if they're like from here, that wouldn't be an estimation.
What would it be instead?
Yeah, that would be exact. So I feel like if you ask them on their opinion, you can, yeah, Kyle's right, basically.
Yeah, so Bree, you're spot on. So Kyle, that's a good idea, but that's asking, it's actually polling the population. If you ask everybody in the class, what do you think about Michigan? Then you're asking every person in the class, and then you're jumping and making an assumption, estimation, different. That's the reason why I want to bring this up, because with statistics, oftentimes people will tell you, I'm sure you guys have encountered that, like 72% of the time I go to the produce department, they're out of raspberries. People throw out random numbers, right? And then you're like, 72, really? Like, have you gone every single time and made a tally? No, they're making an estimate, but is it actually an estimate or is it an assumption, right? So you're inserting a piece of stats, but if it's not based on anything, it's not good, right? Assumptions is not where we want to go with statistics or research at large. Okay, so estimations, hugely important. If we wanted to know if people in our class were born and raised in Grand Rapids, what we could do is ask a sample of them, let's say 3 students, figure out what the percentage was, and then from there on, we can estimate based on the number of people are in the class. Or I can take a look at the population data, right? And say in the state of Michigan, how many people spend their life in the city they were born, come up with that percentage, which is based on the population, and then create an estimate for my sample. That would be another way I could go about it. But both of those estimates are based on actual data, right? Whether I'm taking a subsample of our class or utilizing Michigan State, data, to then make sense or understand the current sample. Okay, so I am teaching, I cannot have you interrupt. So sorry, as I described earlier, I've got little people at home today. Okay, so estimation is a process by which we select a random sample from a population and then use a sample statistic. What is a sample statistic? Do we remember what that is? Sample statistic could be what? Mean, right? Standard deviation. And then we utilize those to then estimate a population parameter. So we kind of have it go back. So for instance, the percentage of Americans who identified as environmentalist, 42% as estimated by a specific poll. And here's their average level of education. And what else does it tell? In the United States, so percentage of Americans who oppose laws. So you take this information and then you are then able to estimate out what that would look like in a specific group. Okay, so this is kind of reiterating the same point. You take a sample proportion to estimate the population proportion. You take a sample mean to estimate the population mean, sample variance for the population variance. So that's really the direction it's heading in every time. And then why do we estimate, which we just talked about a minute ago? It's because most of the time we cannot gather the entire data that would be necessary to fully grasp a population. We just don't have the bandwidth, time, finances to do that. So again, the goal when we think about sampling theory is to actually make statistical inference or estimates based on unknown population, based again on our sample. So we utilize our sample to then broaden out and understand a population parameter. Okay, a point estimate is a sample statistics that's used to estimate the exact value of a population parameter. So that is a point estimate. So for instance, if Gallup is reporting 42% of Americans identify as environmentalists, they're using a point estimate, okay? Because they have gathered a sample, they asked the number of people right here, how many are environmentalists, and now from that, they're generalizing out to the population at large. Again, they're using a point estimate to estimate the number of years of education within that poll. Now, part of the problem can be that sample statistics will vary from one sample to the other, right? So if I asked in our class in statistics how many were born and raised in Grand Rapids, the answer might be different than somebody who is taking you know, in a different class, let's say, like that's, I'm trying to think what would be specific or maybe more different. Then somebody who's taking English as a second language class, right?
Yeah, that works.
So that would be greatly different. Like the chances are that somebody who's enrolled in English as a second language and that they were born and raised in Grand Rapids, my estimate, my assumption is that that would be very, very low, right? Because why would they be in that class? So just something to be mindful of when we think about that.
Can I ask a quick question?
Of course.
I'm a little bit, so how can an estimation be exact versus a quote normal estimation?
So by definition, an estimate can never be exact. It is an estimate, and it will come with something that's called a confidence level or some sort of variability measure, which is called a confidence interval. So for instance, on election night, when you hear 32% of voters response are in and 122 votes went for this candidate plus or minus 4 votes. Like, right, like you might see that in the reporting, the plus or minus. That is what's called your error term, and that's what's creating that confidence interval. Because they know they are estimating, then they give you this range where they're like, we're pretty sure, like we're 95, we'll talk about that again, like a confidence level. We're 95% sure that the answer is right in this range. Now, we don't know exactly which number it is, but we're 95% sure they're right in here.
Okay.
Does that help?
Yes.
Okay. And then with any sample, like I just mentioned, sometimes you may have some variability or a skewed sample that is not going to give you accurate information for your population. So taking it one step back, when you're trying to estimate a population, you have to be thoughtful about who you are sampling, because that'll have an impact, obviously. Okay. So as I just mentioned, because there's that variability within sample, there's always going to be some sort of sampling error or standard error that we need to keep in mind of. So since we don't know how accurate our numbers are in relation to the population, we need to keep that in mind, the confidence level, which we'll talk about again. I'm jumping ahead. This last section here on the slide, that does speak exactly to that. So the interval estimate is the preferred method of estimation because it's identifying a range where the population parameter might exist. So it's again saying this is the range. We are fairly confident that it's right between them. Okay. All right. Next slide over. Can you guys hear me?
Yep.
Okay. All right. So what is a confidence interval? A confidence interval is a range of values that's defined by the confidence level within which the population parameter is estimated to fall. Lots of keywords here. So confidence level, that's going to be a percentage. It's going to be usually 90%, 95%, or 99%. That's the confidence level we're giving it. And then the confidence interval, that's the range, right? That's another way to think about it is margin of error, right? So we're 99% confident that the answer can be found within this range. So again, that's really, really powerful when you think about estimates, because it allows you to really plop down where the population might exist without knowing the exact value, but utilizing some of your sampling data. So confidence level, I just talked about that. So again, that's going to vary between 90%, 95%, and 99%. Now, folks, this is a stats class, right? So what do most statisticians, they go with 95%. Very few will go to 99%. That's really a high level of accuracy. And if you think about it, the higher you go in confidence, the smaller your margin. Okay, so I want you guys to think about that conceptually, right? The more confident I am, right, my margin is going to be low. So we need to be mindful of that in terms of numbers, and then we'll talk about how we get to that in a minute. So for a 95% confidence interval, we have a 5% margin of error, which means there's a 5% chance of not containing the population parameter within our interval. Okay. Is this all making sense so far? Okay. Okay. So again, if you're using inferences, you could see here is a sample of Americans, right? I can calculate a sample mean and a sample standard deviation. This was for the example in terms of the number of years of education. So 13.77 years of education. Then I infer about the general population, and I find that the range is 12 to 14. So I could say I am 95% confident that the number of years of education that Americans possess is between 12 and 14. Now you're probably wondering, like, how in the world did you come up with that? And we'll talk about that in a minute with the math. Okay. So again, why do we care about doing that? Because as soon as we have that and we have an estimate of the entire population, we can start making some inferences and draw conclusions about the population, right? Because otherwise we have nothing to go on. Okay, so when you think about inferential statistics, you are inferring some sort of statistics from it. First, you look at the distribution. So if there's variation in a larger group that we want to know about, that is important too. So great variance, that's going to be harder to estimate, right? if you think about the distribution of the sample observation, so you look again at what is my sample looking like and how much variability is there within my sample. And then specifically your sampling distribution, is it a normal distribution that has a mean and standard deviation that's not going to be impacted by the parameters of your population? So something to keep in mind. Again, big picture is that we all go back to the central limit theorem, which we've talked about this semester, which is that even if a population somehow is skewed, we know that the sampling distribution of the mean will be normally distributed. So as the sample size gets larger, the mean of the sampling distribution becomes more and more similar to the population mean. And again, as it gets larger, the standard error of the mean shrinks. So if you have a tiny, tiny sample, there's going to be more error because we can't be certain that it's not just a sample specific result, right? Okay. Now, researchers do not usually conduct repeated samples of the same population. That's just not something that is very, again, cost effective to keep polling the same group. So they use knowledge of theoretical sampling distribution, and then they construct from their confidence intervals around those estimates so that they can speak on those topics with more confidence. So again, the confidence level is the likelihood expressed as a percentage or a probability. Usually it's a percentage, so it'll be like 95 or 90% confident that a specified interval will contain the population parameter. Okay, so 95% confidence level, what does that actually mean? It means there is a 0.95 probability that a specified interval does contain the population mean. So this, I've said this again, but if you flip it around, then it means that there's 5 chances out of 100 that the interval does not contain the population mean, which those are odds that most statisticians and researchers are comfortable taking, right? The whole goal, if you guys remember us talking about what is statistically significant, is to understand that our data is not due to chance, right? That we have made an effective prediction or an estimate, and the population parameter will land within that. Okay, so on the flip side too, 99% confidence means that there is 1 chance out of 100 that the interval does not contain the population mean. And so what would it be like for 90% confidence? Not meant to be a trick question here.
10 chances out of 100.
You got it, exactly. 10 chances out of 100. Good. All right. So how do we use confidence intervals and how are they constructed? So we use a sample mean. So we'll take a sample, right? Figure out what the mean is for that sample. And then we figure out a point estimate of the population mean. You also will need the sample standard deviation. And that is, again, a point estimate of the population standard deviation. And then finally, you're going to get a standard error of the mean. So you're able to figure out the tails of the confidence interval. Okay, so let's look at what it actually looks like visually. So again, here's your mean. You're right there in the middle, right? Then you figure out here, this is the actual population parameter. Somewhere out here, somewhere within this range is the actual population parameter. And then that is our confidence interval right through here. Okay, so this would be, what is the average shoe size of women? Maybe it'll be 7 plus or minus 0.75. I know, I'm making stuff up. So this would be your mean, 7. And then if it's 0.75, then this would be 7.75 because you would add the 0.75. And if I reduce it, then this would be 6.25. So I would say in the US, I am 95% confident that the average woman in the United States has a shoe size between 6.25 and 7.75. Picked a super random example that probably doesn't make sense with shoe sizes, but does that, do you guys kind of get what I'm saying?
Yeah.
Okay, questions about this so far where you're like, ooh, I'm not tracking. So far, so good? Okay, let's go a little further.
I do have a question. Okay.
Oh yeah,
so
thank you, Brie.
in the confidence interval, is it always in between the first, like the first, I don't know how to explain it. The first interval, I mean, the first standard deviation above and the first one below. Is it always like that?
Oh, really, really great question. So we have been talking in terms of standard deviation when you look at like a z-table, for instance, or a normal distribution, right? Like a normal curve. This is actually not the standard deviation. This is the standard error. So if I would be calculating the standard error, which is based on the standard deviation, to add it to the mean.
Okay.
And I'll show you how we do that in just a minute.
Okay, so it's different. Okay.
Yeah. Here it is. So standard error. So standard error of the mean is the standard deviation of a sampling distribution of the means. It's how much does the sampling mean differ from the actual population mean. And this is actually different than the standard deviation of a sample. So here's a standard error of the sampling distribution. So this is what that would be. You would take your standard deviation and divide it by the square root of n, which again, n is our sample, is our, yeah, the size of the sample, I should say, or in this case, the population. Okay, so this is based on past information that we know, right? We know that the 68% of all random samples will fall within plus or minus 1 standard deviation of the true population mean. Do you guys remember that, right? From the exam, you draw the normal curve, first set of standard deviation, here you are at 68%. Second set of standard deviation, you're at 95%, okay? Now, I'm using standard deviation, which I shouldn't be, standard error. And then you can see here, these are actually z-scores. Do they look kind of familiar? Like 1.96, that's a random number. That's because that's back to z-scores. So 95% of all random sample means will fall between plus or minus 1.96 standard errors of the true population mean. And then the third one for 99%, it's plus or minus 2.58 standard errors of the true population mean. So that's how we divide them up. These numbers are always going to be the same. So again, you're not going to be referring back to a z-table to find it. Those are just given numbers that remain. Okay, so let's talk about how do we estimate the standard error. Usually, standard error is not given to you for a population, right? You don't know what it is. You have to figure it out. So we do the estimated standard error. So that's for a sample, and we again divide by the square root of the sample size, or your n. Okay, so if you see here, this is your standard, your estimated standard error, this S sub y prime. And now we calculate a confidence interval by introducing this number right here, right? And doing a plus or minus z-score. This is going to be for the acceptable error. Again, this may make no sense right now. Rest assured, it'll all come together. And then I think I said it backwards here. This is your mean plus or minus the acceptable error times your estimated standard error. That's what that is. That gives you your confidence interval. Okay. So let's break it down a little bit more. First, you need to figure out what is your sample mean. Next, you need to calculate the standard error of the mean. Third, you're going to decide on the level of confidence, most often 95%, but that needs to be decided also. And what is the corresponding z-value with that? Next, you calculate the confidence interval. And lastly, you interpret the results. So let's walk it through an example, and I think it'll all start gelling together. So let's say you have some questions as to a college campus and college behavior. So there's 15,000 commuters that are coming on campus. You cannot test them all because that would be bananas. You decide to randomly sample 500 of them and ask them how many hours per week do they commute, right? You're trying to figure out how long does it take them to come to and from campus. You get the mean of their scores, which is 7.5 hours per week, right? So you asked all 500, right? Ask them how long does it take you to commute to and from school during 1 week, and your mean was 7.5 hours per week, okay? You have a very large sample size because 500 is not itty bitty. So we're feeling pretty confident that the sample will actually mimic the population mean. And based on the central limits theorem, which we just talked about, we know that the larger your sample size, the more it'll mimic, again, your population distribution and means. But we want to know what is the interval that would capture our true population mean. Okay, so I would calculate the standard error of the mean based on the sample standard deviation, which we're using an estimate for the population standard deviation. Okay, so this would be my total sample is 500. I'm doing the square root of it. And this is my, I'm actually using an estimate of the population standard deviation, which will be 1.5. That's my standard, again, we're just estimating it. And that gives me a response or an answer of 0.07. Okay, so that is step one. Next, I'm going to figure out a confidence level, right? And these are the corresponding z-values for each. We talked about that in just a minute ago, okay? These are the z-values that we will need to plug in based on the according confidence level. So I continue through. Let's say I decide to do 95%, which honestly, guys, it'll be 99% of the time you'll be doing 95%. You want to calculate the z-value at 95%. We know that z-value is 1.96, and I know that because I just showed it to you right here. Don't have to guess it. I will say if I split it, remember we talked about splitting it in half. So at 95%, I have 5% that's not accounted for. Split that in half, it's 2.5, 2.5. Okay, those are my two tails. And then I'm able to see exactly how I would calculate that. So back over here, let's go back a couple. I know here that my estimate of my population standard deviation is 0.07. So that is this value right here, times 1.96, which is the z-value for a 95% confidence interval. I multiply that first, and then it's plus or minus my sample mean, which is 7.5 hours that they're commuting, okay? Which then gives me this range, 7.36 to 7.64. Okay, which then tells me I am 95% confident that if I'm trying to figure out how many hours per week my commuters on campus drive, it is going to be between 7.36 to 7.64 hours per week.
So does it honestly really matter if you use like 90 or 99 or?
Tell me what you mean by matter.
Like, okay, so you were saying like you'll use 95% all the time, but like what, I don't know how I like want to stage this question, but like I don't know, but because there's different options, but like how do you tell which one you use?
Yes. So I would say almost every time you're going to use 95%. That's just the gold standard in the world of statistics and research. The only time you would do 99%, that's usually when you, if somehow you've either figured out that you have a statistical difference, right? So, because remember again, a p-value can be less than 0.010001. You might insert it that way, but honestly, 95% is what you're going to use most often. I feel like I'm not giving you a very helpful answer as to why we do that. There's just different options, but 95 is the most common one.
Okay, I'm gonna just have to put it in my head. That's just how you do it.
95, yes. And 1.96, two things glued together. Okay, so my confidence level, again, if we were to actually do exactly what you're asking, like why 95, we can increase our confidence from 95 to 99, meaning I don't want to have the wrong conclusion. I really want to be really, really certain. We want to reduce the risk of being wrong. So if we're reducing the risk, inherently the range is going to be a little higher, right? Like if you're, say, I want to really make sure that I got this correct, making it a little wider is going to make it more sure. Okay, so then that would look like this 2.58. So remember over here, we did 1.96. If I want 99%, then I'm at 2.58. I do the exact same calculation, and the range is 7.32 to 7.68.
Okay, it's just a matter of like how right you want to be, basically.
Yeah. Like if you said 50%, I don't know why you'd want to do that, right? Like half and half, this could be right, could be wrong, right? 95% is usually seen as like a strong enough, powerful enough like estimate. Occasionally people will say 99%. But just so you know how to do it, like in terms of calculation, you just substitute one number, which is that Z value, okay? So the value went from 1.96 to 2.58.
It wasn't really the matter of like how you do it. It was just a matter of why.
Yeah. I don't have a good answer as to why. It's just, again, how right do you want to be? But 95 is usually good enough. So you could always strive for 100, but again, why? Sorry for all the squeaky noise, you guys. Thank you for your grace and patience. There's a new toy and she's got to squeak it. Okay.
Puppy, we get it.
Yeah, I know. Puppy. Well, the puppy's sleeping. It's it's the 5-year-old doggy that's
5-year-old
just
can play too.
Yeah,
Yeah,
I guess
fun.
so. I mean, look, she just looks she's having so much fun. So much fun. Well, now she's stopping just to prove me wrong. That's how it goes. All right. So if we look here, 95% confidence level versus 99, it just widens a tiny bit. Again, 95 is plenty. That's usually plenty good in terms of limiting error. And that's the range that we usually will go with in this class and anywhere in statistics that you see. Okay. Now, are we actually, when we think about confidence interval and why we pick a range, it's because we're trying to reduce the risk that the actual population stands outside of that range, right? We're trying to be really as sure as possible. So if I know these are the values, right? It ranges from like 32 to 7.68. I can then take several different other samples, right, from that to try to figure out the true population mean. And based on all of these, then the true population mean would lie somewhere around 7.6, which that's falling right in our range. So that would be okay. All right. So again, to reiterate, I feel like I'm doing a lot of to reiterate, but just to make sure we're all on the same page, the way you would describe that would be, we are 95% sure that the mean of the population for commute time for students at University X lies within the range of 7.36 to 7.64. But that does mean there is a 5% chance that it's actually outside of that range. Similarly, if I did the 95% confidence interval, I would say I'm 99% sure that the population mean of commuting time per week for University X lies between 7.32 and 7.68. Okay, but again, there's still a 1% chance that it lies outside of that range. Okay, so that's how we would illustrate that and explain that away. Questions about all that?
Okay, so kind of just a little bit of a different way of thinking. So is this where like companies come into play where they just frame things in a way that like suits them better? Like, oh, 99% of our customers use our product and love it. Colgate. And that's where like all the, you know, toothpaste commercials can say, oh, we're the best. But like, I mean, every toothpaste commercial says it.
They totally do. So yes, because with confidence interval, you certainly could do a poll and ask on average, it's usually going to be for something you can run a statistic, not necessarily like because if you think about the brand of toothpaste, that's going to be a nominal choice, right? Colgate, Crest,
True.
Aquadent, whatever the other ones are, Sensodyne. So that's going to be more of a nominal response. It would be more of something to do mathematically, like on average, people own 7 cars in their lifetime. We are 99% confident that on average, the average American owns 7.2 cars in their lifetime with a confidence interval of 6.8 to 8.5, right? And so then there's a 5% chance that they might be wrong, right? Like that if we actually asked every single person that lived in the United States and got an average, that might be different than what they came up with based on their sample. So there is a possibility to manipulate data for sure. That is sadly part of the game anytime you have stats. All right. No problem. All right, so if you think about sample size, that impacts things too. We talked about that already a little bit, but the larger your samples results in a smaller standard error. Okay, in other words, the larger my sample, the more likely it's going to mimic the population. Therefore, the smaller my standard error is going to be. So, and again, it's because of the central limit theorem, they kind of mimic one another. So, standard deviations, very similar. So a smaller sample standard deviation results in a smaller, more precise confidence interval. So unlike sample size and confidence level, the researcher plays no role in determining the standard deviation of a sample, right? Standard deviation is just what it is. The researcher has no impact on that. It's just a gathering of data. All right, so let's use this example. This is a TV watching example. So the General Social Survey sampled 1,001 people and asked how many hours a day do Americans spend watching television, okay? The average based on those 1,001, not just 1,000, that one needed to stay in there, is 2.94 hours with a standard deviation of 2.6, okay? We use the sample standard deviation as an estimate for the population standard deviation. And the reason why we can do that is because our sample is 1,000 people. That is a large sample. If we had a sample of 50 people, that would be a little trickier. So in examples that I give you, you're always going to be able to use the sample standard deviation as an estimate of your population standard deviation. Okay, so then I calculate that, it'd be 2.60 divided by the square root of 1,001, which gives you a standard error of 0.08. Okay, next up, I need to make some decisions. I'm gonna first pick a confidence level, which is gonna be 95%, and then I'm gonna take a peek at what is the corresponding z-score. Corresponding z-score for 95% is 1.96. And then I just plug in the data. So 2.94 is my sample mean. It's plus or minus the product of my z-score, 1.96, times the standard error, or the standard error of my sample, which is 0.08. That gives me a range or a confidence interval of 2.78 to 3.10. Okay, quick little tidbit here. This was an issue with students last year, and I didn't think to check with you guys, but you can always verify your work by making sure, first off, that your mean is found between the interval. Occasionally, people would do weird math, and like this would end up being 3.5 to 4.2. And I'm like, but hold up here, your mean was 2.94. How did you end up with a confidence interval that's outside of the mean? That's very unlikely to happen. Your mean should be somewhere in between there, because if you think about it, your mean is right here and you're adding this number and then subtracting that number. So inherently, it's going to be right smack in the middle. Okay, so that's another quick fact check. If somehow you're working quickly and making a mathematical error, know that your mean should be in the middle of your confidence interval. Okay, first, let me just go back. Did that make sense? Did everybody kind of follow through this example?
Sounds good.
Questions? No? Okay, let's power through. So this is our TV watching example. We can increase the precision by increasing our sample size. So if you see, and we can do the reverse the other way around. So if I increase my sample to 1987, then you can see my confidence interval has just tightened, right? I went from 2.78 to 3.1 to 2.82 to 306. So it's getting more precise with it, okay? Conversely, if I reduce my sample size and I reduce it to 150, notice how my band just expanded. With a smaller sample, I am less confident that my sample mean is going to reflect or estimate my population mean. Okay, and that's all calculated, if you see here, by creating the standard error. So you see the standard error that we calculated earlier for 1001 was 0.08. If it's 1987, it turns to 0.06. If it's 150, it increases to 0.21. Okay.
Okay, so quick question.
Mm-hmm.
So for the sample size, is there like a direct correlation with like from sample size to S mean? Is like the first column and the last column?
Yep.
Is there like a chart where we like if we had a sample size of 250, what would our other number? What would the corresponding number become?
Yep. So you could actually calculate it. It
Okay.
wouldn't be a chart, because here's the only thing you're changing here, Kyle. Just this number underneath the square root. That's the only part. So your standard deviation remains the same. You're just switching this number around, which is impacting the standard error.
All right, perfect. Thank you. That's all I
Yeah,
need.
and then you're taking that standard error and multiplying it by your z-score. That number's not changing. And then you're doing plus or minus your mean. So you're just increasing the width or decreasing the width of your interval.
All right, awesome. Got it.
Yeah. No, good question. Okay. So now if we did a 99% confidence interval, we go through the exact same process. So I start by figuring out my standard error. And now I'm going to use the higher number right here, right? The 1987. So you can say I plug that in. That gives me a standard error of 0.06. This should be here. Oh, I think this is for you guys to do it on your own, because this is still 95. So what would be the difference? What would be this number? Do you guys remember?
2.94.
2.94 is my mean.
Oh, shoot. Yeah, you're right.
Yeah. So what is the z-score for 99% confident? Do you guys remember that? So 90% was 1.6. Oh, go ahead. Yeah.
2.58.
2.58 is the right number. Okay, so let's calculate it as a team here. So the way you'd calculate it, right? Grab your handy dandy calculator. You're doing 2.58 times 0.06. Everyone should be able to calculate that. That should be 0.15. Everybody thumbs up, they calculated that correctly?
Double thumbs up.
Okay. How about the non-Kyles of the class? Everybody else tracking? Otherwise, Kyle and I are having a great tutoring session. Okay, I'll assume that's a yes. Then the next part is you would want to add your mean. So add 2.94. So that gives you an upper bracket for your interval of 3.09. Okay. Next step is I want to take 2.94 and I want to take away 0.15, right? That was the value that we had earlier, which is 2.79. And then we end up with our range or our confidence interval. Everybody good with that? Okay.
Yeah.
Yes. Go. Was that a yes or a question, Elizabeth?
It was a yes.
Okay. It was kind of a drawn out. Yeah, I was like.
Yeah, I'm lagging behind a little bit, to be honest, but I'll catch up.
Okay. Okay. So the whole point, again, of the reason why we do that and I want you guys to keep that in mind, is that we have a sample and we want to be able to generalize to the population at large. That's always the name of the game. So if you have an interval width that is fairly wide, right, then the way you're predicting things is going to be not quite as accurate, okay? So if you look here, if my n is 195, it's a smaller n, right? My confidence interval is not very precise. You see it's much wider. As your n increases, the larger your sample size, the tighter your confidence interval becomes and the more precise it becomes, okay? So you can see here that there's very much a relationship between your sample size and your overall confidence interval, okay? Now, something else to be mindful of. There comes a point of kind of limiting gains, right? Or diminishing returns, another way, which is why in research, right, I can tell my doctoral students, the more the better. You should go and recruit 5,000 people. First off, they will never graduate with their PhD and they'll hate me forever. So don't want to do that. But I also will not allow them to just do a survey of 50 people, because the data that you get from that is not very meaningful. So you need to strike a balance, and you need to recognize once you get to a point where you're like 500 plus, the tightness and how much more precise you are in predicting, it's not like a 1-to-1 ratio. Like with every 10 extra people, then the more 10% more precise I am. No, it's just really a small difference. So is there ever a need to collect data from 10,000 people? My answer is no, there is never a need for that, because then you are approaching the population so closely that you're not really estimating, you're almost getting the population. So kind of what's the point? So save yourself time, save yourself money, create a smaller sample, but a significant enough sample that you have power within the data you're gathering. Okay, that's my soapbox for a hot minute there. Okay, so I feel like we're describing a slightly different study here in your textbook. So here's the study that they looked at. So there's nearly 55 million people that are of Hispanic or Latino descent or ethnicity in the United States. This is polled in 2014. So we want to take a peek at what it looks like to see there's studies between earnings between the groups. So we want to look at the gap in earnings. This is again from your textbook. So in this study, the researchers argued that Mexicans, Puerto Ricans, and Cubans varied markedly in their socioeconomic characteristic because of differences in their timing and circumstances in the immigration process of the United States. Okay, you can read more about kind of historically why that is. They noted that only about 9% of Mexicans and 60% of Puerto Ricans have graduated college compared with 25% of Cuban men. So these differences in migrant status and educational level were likely to be reflected in disparities in earnings among the three groups. So what they did is they figured out, they grabbed a sample. First off, they had a sample for each of those groups. You can see the ends are written there. So for Mexicans, it was 34,620. So on and so forth for Cubans and Puerto Ricans. They asked them, what is your income? And that income mean was calculated. You can see the sample mean for each. Here they are. And then they added with that the standard error, which was multiplied here, okay? And that is how they were able to get each of these confidence intervals. Now, something that's kind of interesting to note is that the confidence intervals do not overlap one another. So they are really in distinct categories. So if we did another statistical analysis on this and we saw how different those groups were, which would be like a chi-square, well, probably a multi-way ANOVA or an analysis of variance, they would be significantly different. There is no overlap in their income mean. Okay, just another example from your textbook. Okay, how are we doing on time? Why don't we take, yeah, let's quick stop here for like 10 minutes. I am going to honestly zoom through some of this proportion piece because we're not going to be practicing that as much. And I'm going to set up our practice for our lab so that you guys know exactly what to do for next week. Sound like a plan?
Yeah.
All right. So let's plan on coming back in 10 minutes. All right. See you guys in a minute.
Thank you.
No problem.